Okay, so today we'll talk about inverses in section 6.5. And then for the second half of the lecture, we'll talk about relations. We'll start talking about relations, which is chapter 7. Okay, so let me just remind you what we did at the very end of last lecture, which was we talked about how you can think about a function as a certain subset of the Cartesian product, right? What you do is for each A in the domain, you have one element with that first coordinate in this subset of the Cartesian product, and the second coordinate of that is what f does to it. Right? So you have like one f of 1, 2 f of 2, 3 f of 3 in this example. But then you said we could consider just any subset of the Cartesian product, right? Like here are two different ones, this g and this h. Those are perfectly fine, perfectly good subsets of the Cartesian product. Of course, they're not going to give functions, because we saw this theorem, which said that you can look at all these different subsets of the Cartesian product. It gives you a function if essentially every element of A appears once and only once as the first coordinate of an element in the subset of the Cartesian product. So functions can be thought of as special subsets of the Cartesian product. But in today's lecture, we'll see that we can just consider any subset of the Cartesian product. It might not be a function, but we can study those too. Okay. So the first thing I'm going to do today is I'm going to define the inverse of a function thought of as a subset of the Cartesian product. Okay, so first, if we consider f a function, we can define the inverse of f. Okay, now key point here is this inverse, I'm not saying that it may or may not be an inverse function. I'll define it in a second. I haven't defined it yet. But for every single function f, right, not every function will be an invertible function, but we'll always be able to define a certain kind of inverse. So let me be precise by just making this definition. So let f from A to B be any function. And consider the subset of the Cartesian product. F is a set of all A, B in A cross B such that f of A equals B. Okay, so this is the usual way to think of a function as a subset of the Cartesian product. That's all I've done here. Now the inverse of f, denoted f inverse, is defined to just be the following set. You just take all B comma A in B cross A such that f of A equals B. And this is essentially what you do is you just take the function and you just flip around all the coordinates. You just swap all the first coordinates with all the second coordinates. This is, of course, a subset of B cross A. Another way to write this is the set of all B comma A in B cross A such that A comma B is an F. So all we've done is we've just swapped all of the entries in F. So we've gotten now a subset of the Cartesian product B cross A. We are definitely overloading this notation, this F inverse. Right? This is abusive notation because we also use F inverse for the pre-image. So we should be clear what thing we mean if we use this notation. Okay. So I guess first we need some examples. So examples. Right, so I think last time we had a function like this that I called f. There were 3 things in the domain, 2 things in the codomain. I think it looked like this. And I'll send 1 and 2 to x and 3 to y. Right, so this is a function f from A to B, where f of 1 equals x, f of 2 equals x, f of 3 equals y. Okay, and then this function we can think of as a subset of the Cartesian product which subset, again, you take an element of A and what it maps to under F, and you do this for every single element of A. And this is how to think of this function F as a subset of the Cartesian product. And then the rule was this inverse is you just flip around all of these ordered pairs, and this is a subset of B cross A. Okay, so that's all I've defined. This is the thing I defined on the last page, this inverse. Okay, but notice that this is not a function, right? Because essentially the way that you can picture this is you can just flip around all of the arrows, right? So this thing that I boxed in blue, if you were to try to picture this in the same way as some kind of arrow diagram, I can just imagine flipping around all the arrows. So x1, x2, y3. This is like what the picture of F inverse looks like, and this is not a function. It's just some subset of B cross A. Okay, so I said we were abusing this F inverse notation because we also meant it for pre-image, but yet another use of F inverse notation is if a function actually has an inverse function, then you use this notation for the inverse function. But I'm using this notation more generally. No matter what function F is, F needs no special properties. I can define this inverse as a subset of a Cartesian product. It always exists. You just flip everything around, but it may or may not give you a function. But that leads to a good question. When is F inverse a function? Or when does it give a function, this process? Okay, well, what was breaking here in this example? The thing that made our inverse not a function was that we had two arrows coming out of X. And the reason that happened was because we had two arrows going into X. In other words, in this example, F inverse was not a function because F was not injective. Right? Because f of 1 equaled f of 2 equals x. This meant that 1 comma x and 2 comma x were both in F, which meant that x comma 1 and x comma 2 were both in F inverse, and this isn't allowed if F inverse is supposed to be a function. So we don't want this to happen if we want F inverse to be a function. Right? So definitely we need F to be injective. Otherwise, this will happen, right? You'll have some situation when you define the inverse, you'll have a first coordinate twice. Now, is that enough? Is it enough to make sure that F is just not an injection? Well, remember, what it means to be a function from an arrow diagram perspective is that you have one and only one arrow coming out of every dot in the domain. That means that if I want F inverse to be a function, in the original picture, right, in order for this blue picture to be a function, in this original picture, it means I need one and only one arrow going into every dot in the codomain. Right? One and only one arrow into every dot in the codomain. So if F is injective, it means that you never have more than one arrow in. But we could have also another problem, right? Another problem. If I make my function injective, what was it? I was using like 1 and 2 here. So here's an injective function, F. Right? But if you think about what it is a subset of the Cartesian product, it's just 1 comma x, 2 comma y. So F inverse would be x comma 1, y comma 2. Right? I guess the picture of F inverse would be like this. Just a sketch. But this is also not a function. Right? It's definitely a subset of B cross A, that's for sure. But it's not a function because for it to be a function, it needs to be defined everywhere on the domain. Right? In this case, the domain of F inverse would be B if it were a function. But the problem is that we don't know what happens to Z, so F inverse is not a function. We need to be able to define a function on all of B. So this means that we need also F, the original F, to be surjective. So we also need to be surjective for F inverse to be a function. Okay, so we need F to be injective. We also need F to be surjective. That means that we need F to be bijective, right? We sort of talked through the proof. So if F inverse is a function, if it's ever going to be a function, this will imply that F is bijective. And in fact, it is actually an if and only if. So you can always define the inverse of any function, no matter what. But the inverse is only a function, it's if and only if the original function was bijective. Then this process gives you a function from B to A. Okay, so let's state this as a theorem and then prove it. We've sort of already proved the forward direction. But here's the theorem. Let F be a function from A to B. The inverse of F inverse, is a function from B to A if and only if F is a bijection. Okay. So I see in my notes that I'm saying that we basically proved this above, but I will give you a full proof in the notes. So let's do this direction first. So suppose that F is a bijection. And let's consider, I guess I should say let's just be very proper. Suppose F is a bijection from A to B. Consider F inverse as a subset of B cross A. I want to show that F inverse is a function, right? Which means that I need to show that F inverse satisfies these two properties for every, okay, but with A and B switched, right? Because this is thinking of F as a function from A to B, but F inverse will be thought of as a function from B to A. So I need to make sure that every element of B appears as a first coordinate in F inverse, and it appears only once as a first coordinate in F inverse. That's what I need. So we need to show that F inverse satisfies the two properties. In your notes, I'm seeing this as theorem 140. I hope that's correct. Sorry, 137. The current one that I'm proving is 140. So the first condition is that I need to make sure that for every single B in B, there is an ordered pair B comma something in F inverse. So suppose that B is in B. Right? What I'm trying to prove is that B comma something is in F inverse. But that's if and only if, right? Something comma B is in F. Now, is this true for every single B? The answer is yes. That's because F is surjective. So I should be able to find something that maps over to B under F. And then that thing will have B as a first coordinate in F inverse. Okay, so this blue is just scratched. I don't want you to think that this is part of the proof. Now, since F is surjective, This means that there exists some a in A such that f of a is equal to this b, this little b that we have. So then a comma b is in f, so b comma a is in f inverse by definition. Therefore, I've shown that it satisfies property 1. No matter which b and b I pick, it appears as the first coordinate of something in f inverse. Now, to prove that f inverse satisfies the second condition said that each element of b is the first coordinate of exactly one ordered pair in f inverse. It was never the first coordinate of two different ordered pairs. So let's let b be in b and suppose that it's the first coordinate of two ordered pairs, b comma a1 and b comma a2 are in f inverse. I need to show that these two ordered pairs are actually the same. Right, so I guess I should say what a1 and a2 are before I do this, and suppose there exists a1 and a2 in A such that b comma a1 and b comma a2 are in f inverse. Okay, this means that a1 comma b and a2 comma b are both in f. So f of a1 equals f of a2 equals b. But now, since f is injective, since f maps a1 and a2 over to the same element, b, it means that a1 and a2 must have been the same element to begin with. Since f is injective, this implies that a1 equals a2. Okay, so we use the surjectivity of f to prove that every b in b appears as the first coordinate of something. Then we use the injectivity of f to prove that if it was the first pair of two things, actually those two things were the same. Right? Maybe that's actually how I should conclude my proof. This implies that b comma a1 equals b comma a2, which is what I want to show. So this shows that if you have a bijection, f inverse will give you a function. F inverse will actually give you a function. Now, for the forward direction, I think I basically talked through this proof as we were discussing these two issues. These two issues sort of show that you have to make sure that f is injective and you have to make sure that f is surjective if f inverse is going to be a function, which is exactly this direction. So let me just give you a sketch. Right, so suppose that f inverse is a function. Again, thought of as a subset of b cross a. But if f inverse is a function, then f inverse satisfies the two properties. In theorem 137, every element of b appears as the first coordinate of something in f inverse, and at most one thing in f inverse. Okay, and what you'll do is you'll say, since f inverse is defined on all of b, this is property 1. This will give you that f is surjective, because every element of b will appear as a first coordinate in f inverse. That means that every element of b appears as a second coordinate in f. That just means that f hits everything in b. And then since f inverse is actually a function, in other words, you never send the same b to two different elements in A, that will give you that f is an injection, and therefore f is a bijection. Okay, that's the proof sketch. You should think through and write up the logic yourself. This will give that f is injective. Right? This one is property 2, basically. And altogether, this will show that f is bijective. And this will finish the result. Okay, so just to recap, we defined the inverse of any function. Given any function, you can define this inverse. And then we just said that this inverse gives you a function in the other direction if and only if f is bijective. Then you can talk about the inverse function. So I should just make this definition. Definition. When f from a to b is a bijection, then we just showed that f inverse gives a function b to a. In this case, we can write that f inverse is a function from b to a, and we can call f an invertible function. Okay? Again, every single function has an inverse in this sense. But the inverse is only a function if f is bijective. So if the inverse of f is a function, we call f an invertible function. Okay, now this is probably not the definition of the inverse that you're used to. Maybe the definition of the inverse that you're used to is that the inverse sort of undoes the function, right? If you do f and then you do f inverse, it's like you did nothing at all. So that will be the content of the next couple of theorems. So if f is a bijection, then this f inverse is a function defined by the following. For every a in a and for every b in b, f of a equals b if and only if f inverse of b equals a. Now this theorem is basically just the definition of f inverse together with the previous theorem, right? So if f is a bijection, then we prove that f inverse from b to a will give you a function. What function does it give you? Well, if a comma b was an f, then b comma a was an f inverse. And this means the same thing as this, and this means the same thing as this. So this is just the previous theorem together with the definition of, how you translate back and forth between a subset of the Cartesian product and a function. Okay, but I state it like this just to have it stated precisely in the notes. But the point I'm trying to make is the following corollary, which is suppose that f from b to a to b is a bijection, then for every x in a, f inverse of f of x equals x, and for every y in b, f of f inverse of b equals b. Sorry, of y equals y. Okay, so this is maybe how some people might define the inverse function, or how you often think of the inverse function. It's just a thing that in some way undoes the original function. So if you have something in A, you apply f inverse, you get back to where you started. And if you have something in B, you apply f inverse, and then you apply f, you get back to where you started. Okay, and the proof is very quick. It's just an exercise in using the definition. So let me just do one for you. So suppose x is an A, and write y equals f of x, right? So I take any x in A, and then I just apply f to it. Let's call that y. Okay, well then x comma y is in f. So y comma x is in f inverse. But this means that f inverse of y equals x. Right? Therefore, let's consider this quantity, f inverse of f of x. By definition, this means you first do f of x, and then you apply f inverse to the output. But f of x is just what we were calling y. And then f inverse of y is just x, which is what we wanted. So you prove that the second part essentially actually has exactly the same proof, but you just start with a y in b, and you just sort of do this process again. Okay? So this inverse, this weird inverse that we defined at the beginning of the lecture does actually correspond to the normal inverse that you're used to if f happens to be a bijection. Then this subset of the Cartesian product will give you the inverse function. But this is more general than the definition of inverse that you're used to from previous classes, because I can define this even if f is not an invertible function. Okay, well, now that we have inverses lying around, I guess we should ask some questions about them. So here's the question. Let's suppose now that I have two functions that are both bijections. That means that they're both invertible. We prove that. So they're invertible, so f inverse and g inverse both make sense. These are both functions. Also, we proved that g of f is a bijection. Did we prove this? If we didn't prove it, you can prove it. You should prove it. I actually don't remember. Did we prove it? If not, it's an exercise. But since g of f is a bijection, it has an inverse. So the question is, what is g of f inverse? Right? F and g are both bijections, so they each have inverses. The composition is a bijection, so it has an inverse. In particular, how is g of f inverse related to f inverse and g inverse? Okay, and the answer is that g of f inverse is equal to f inverse of g inverse. In other words, you have to flip around the order. Okay, well, why is this? So the flipping of the order is actually not so easy. I mean, it's not so hard to see why. So here's one way to think about it. You just think about where f and g go from and to, right? So f goes from a to b and g goes from b to c. So g of f goes from a to c, right? F inverse goes from b to a, and g inverse goes from c to b, and g of f inverse goes from c to a. So g of f inverse, if it's like the natural guess here is you first do g inverse and then you do f inverse, if you look at this picture, which is exactly what this is. This says first do g inverse and then do f inverse. So that's one way to think about it. Another way to think about it is imagine that like f is the function like of putting on shoes. It's a function from you to yourself where you put on shoes. Sorry, let's say socks, just to make this make more sense. And g is the function putting on shoes. Right, then g of f, that means first do f, then do g. That means first put on your socks and then put on your shoes. How do you undo that? The way that you undo it is you first take off your shoes, then you take off your socks. Right, so g of f equals put on socks, then shoes. So G of F inverse should be take off shoes, then socks. The order switches, which is going to be you first take off your shoes, that's G inverse, and then you take off your socks, that's F inverse. Okay, the third way to think about it is, if you remember from Math 308, if you have two matrices that are square and invertible, if you want to take their inverse, AB inverse, then you have to take B inverse, A inverse. You have to switch the order, because when you go in the opposite direction, you have to do things in the opposite order, essentially. Okay, but this is just a sketch and sort of an intuition. We should actually just prove this. So suppose that F from A to B and G from B to C are bijections. Then for all Z and C, G of F inverse of Z is equal to F inverse of G inverse of Z. This just says that the function G of F inverse is the same thing as F inverse of G inverse. We did prove that G of F is a bijection. It was a corollary. I'm now seeing it in this proof that I'm about to give, so that's good. Okay, so since F and G are bijections, we proved that G of F is a bijection. Okay, because the codomain of F is the same thing as the domain of G. Okay, now let Z be any element in C. We want to understand what the inverse of G of F does to Z. Okay, so suppose, let's just call this G of F inverse applied to Z, let's call it X. This is an element in A. What does this mean? This means exactly that if you apply G of F to X, you get Z. That's how the inverse was essentially defined, right? If a function applied to X gives you Z, then the inverse function applied to Z gives you X. What do we want to prove? We want to show that actually F inverse of G inverse of Z is our X. That's what I want to show, right? Because, like I said, let me just say this again. I'm just calling X whatever G of F inverse of Z is. I'm trying to prove that it's equal to this. So I'm trying to prove that X is this thing. Okay. But since G of F of X equals Z, this means that G of F of X equals Z. Call F of X Y, then G of Y is equal to Z. Right? Now, again, all these functions are invertible. So if I'm calling F of X Y and G of Y Z, then F inverse of Y equals X and G inverse of Z equals Y. And this means that F inverse of G inverse of Z is F inverse of Y, which is X. Right, hence, G of F inverse of Z, which is what I was calling X, is equal to F inverse of G inverse of Z, which is what I was trying to show. Okay, so seems a little bit convoluted, but everything that I said here was true and it proves the result. So then I guess that means that the proof is correct. Okay, so that's what I want to say about inverse functions for now. But let me go once again back to this first slide, as I have continually been doing this lecture. One question is, what if the inverse is not a function? In other words, if f isn't bijective, I can still define the subset of the Cartesian product. But if it's not, if f isn't a bijection, then the inverse is not a function. But shouldn't I still be able to study it? Shouldn't I still be able to understand it in some way? And the answer is yes. If f is not bijective, or if f is bijective, but even if it's not bijective, the inverse may or may not be a function, but it is an example of what we call a relation. So this is the contents of chapter 7 on relations. So I still have about 13 minutes or so to talk about these, so I'll get started. So recall, I mean, it's just earlier this lecture, if f from a to b is a function, f is a subset of a cross b, and then the inverse is a subset of b cross a, which is not necessarily a function. It may or may not be. However, this thing is always what we'll call a relation. Okay, also a function is also an example of a relation. So roughly speaking, what a relation does is it just relates elements of one set to another set. That's all it does. It just relates elements of one set to another set. So for a function from a to b, we related each element of a to exactly one element of b. Right? You can think of a function as just relating elements of a to some elements of b. But of course, you could choose to relate an element of one set to more than one element of another set. That's the idea of what a relation captures. In other words, a relation will exactly capture sort of every single possible arrow diagram between a and b, even if they're not functions. Okay, so let me give you the precise proper definition. Let a and b be sets. A relation, which I'll call R from a to b, is just defined to be a subset of a cross b. Any old subset of a cross b is something that I'll call a relation. So of course now f and f inverse will both always be relations because they're both some subsets of a Cartesian product. Okay, now a relation from the set A to itself is called a relation on the set A. So that's the special case. It's just a subset of A cross A. So you can define a relation just between any two sets that you want. But if you have a relation from a set to itself, I call that a relation on the set. Okay, so let's just start with some examples. I owe you lots of examples, I think. So let's just start with a small, very artificial example. So let's let A be 125, B be 047. Let's define a relation. Let's define a relation R from A to B by x comma y is in R. Remember, the relation is just a subset of the Cartesian product if and only if x minus y is even. So what I'm doing is I'm just picking out a certain subset of Cartesian product. Which subset of the Cartesian product? It's the subset where the difference between the elements is even. Okay, so first let's write down the whole Cartesian product. Right? So the whole Cartesian product is every possible combination. So 1, 0, 1, 4, 1, 7, 2, 0, 2 comma 4, 2 comma 7, and then 5 comma 0, 5 comma 4, 5 comma 7. That's the whole Cartesian product. That's every possible ordered pair. What is the relation? The relation is just the subset of the Cartesian product where the difference between the x coordinate and the y coordinate is even. So which things are in the relation? This one, this one, this one, and this one. So the relation is just 1 comma 7, 2 comma 0, 2 comma 4, 5 comma 7. That's the first example of a relation. This is a subset of A cross B. Okay, and one thing that you can think about this as is this relation, what's doing is it's relating elements of A to elements of B that have the same parity, right? I'm taking all the odd elements of A and relating them to all the odd elements of B. That's these two. I'm taking all the even elements of A and I'm relating them to all the even elements of B. So what this is really doing is this is relating elements of A to elements of B with the same parity. That's one way to think about what it's doing. Okay, so this is kind of an artificial example, but still a reasonable one. Let me give you a more natural example, one that naturally comes up. So a natural example. Okay, so let's let our set A and our set B both be Z. So I'm going to define a relation on Z, the set of integers. We'll define a which will be given by congruence modulo 5. Right? Because we're already used to think of congruence modulo 5 as relating one integer to another. Right? So we already are used to thinking about this as relating certain integers to one another. Right? We're used to thinking of, oh yeah, 2 is congruent to 7 is congruent to -3 modulo 5. Another way I can think of this is, oh, I'm relating 2 to 7, and I'm relating 2 to -3, and I'm relating 7 to -3. These numbers are all related to one another by being congruent modulo 5. Similarly, 0 is congruent to 5, it's congruent to 10, it's congruent to -5, it's congruent to 100. Those numbers are all related to each other in that they have the same value modulo 5. They're all congruent modulo 5. So we can now think of this as a subset of Z cross Z. Let's define our relation R by, this is not what R looks like. Let's define R by A comma B is in R if and only if A is congruent to B modulo 5. So I'm taking a subset of the Cartesian product. Which subset? I'm taking all the pairs where both of the coordinates are congruent to one another modulo 5. That's the subset of the Cartesian product that I'm taking. And this is a humongous subset of the Cartesian product, I should add. There's tons and tons and tons of elements in this Cartesian product, in this subset of the Cartesian product. Right, so let's just list some things in R. R contains, for example, 0, 0, because 0 is congruent to 0 modulo 5. It also contains 0, 5. It contains 0, 10. It contains 5, 10. Right? It contains like 2, 102. Those are equivalent modulo 5. Right? 3, -2. Those are related modulo 5. 2, 7. There's tons and tons of elements in here. It's some humongous subset of Z cross Z, where you've listed every single pair of elements that are congruent modulo 5. And so, yeah, this is an example of a very natural relation. We're used to thinking of congruence modulo 5 as relating to an integer to another integer. I can now think of it as a big subset of z cross z. Okay, so I think perhaps I'll stop here. I do have one more example, or actually a few more examples, but maybe I'll let you sit on this until the next lecture. And in the next lecture, we'll really start diving into relations. Okay, so like I said, I kind of like starting a new thing at the end of the lecture and then trying to refresh it at the beginning of the last lecture. We define a very, very general notion. A relation is just a subset of the Cartesian product. But congruence modulo 5, I can think of it in terms of a relation. And it turns out there will be many, many more very natural notions of relations. So if we study relations, we can learn about all these things all at once. Okay, so I'll leave it there. We'll continue in chapter 7 at the next lecture.